All right, let's go through a simple power cycle and do an example. So we're going to sketch out the diagram in a second, but basically it follows, well, here, it's going to follow this idea without these numbers, where I have something going into a turbine, into a condenser, into a pump, into a boiler, and coming back. Okay, that's the idea. And what we're going to do is basically, we know that the superheated steam at 6 megapascals and 540 degrees Celsius flows into a turbine. So basically, this is stream number one. It's 6 megapascals and 540 C, and it's going to go into this turbine, and the turbine is going to produce some work. And it's going to produce 10 megawatts of power. And then it will exit at these conditions, 0.008 megapascals and a quality of 0.9. So that's stream number two here. These are not the correct numbers. It's going to be 0.008 megapascals and this quality. And then it's going to go into a condenser right here, which will fully convert this saturated mix into saturated liquid at the same P and T. So now we have information about stream number three, which comes out of the condenser. And then after it goes to the condenser, this liquid is finally fed into a boiler, which recovers the initial stream. So after it comes out of the pump, it's going to go into a boiler and go into the final stream. Okay. And we need to figure out the mass flow rate, the work of the pump, the work of the turbine, the heat out of the pump, and the heat out of the condenser. So we're going to provide heat here. So it's going to be positive. This is going to be negative out of the condenser. The work of the turbine is going to come out. So it's going to be positive. It's going to be something that we can use. And we have to provide the work into the pump. So it's going to be negative. And then we were asked for the percent of the heat that's being input into the boiler. What percent of this heat is converted into net work? Okay. And so that's basically what we got to sketch out. So what I do each and every time when I have questions like this is define my states, because I need the state variables to calculate things that are not measurable. So we'll start state one, and then we'll have state two, state three, and state four. And obviously we have four states because we have this pressurized steam coming in, that's state one, state two coming out of the turbine, state three coming out of the condenser, and step four coming out of the pump. And then after the boiler, it becomes stream one again. So we have these four states. And what I'm going to do is, I really need a lot of the H's, but I'll put the V prime as well. Maybe we need it. We don't know. The temperature and the pressure. And we will start obviously what we have. So we know that at state number one, we have 6 megapascals and 540 Celsius. So what I suggest doing for any of these questions is to directly use SI units so that it's not hard to get the answer at the end, not deal with all the silliness of it. So 6 megapascals is 6 million pascals. And we know that the temperature is 540. You could leave it as Celsius. And you can easily convert that to Kelvin if you need to. Okay, I don't have the V bar. I don't have the H bar. What do? Well, I know it's superheated. So I'm going to go to the superheated steam table that I have conveniently open right here. And I know that I am at 6 megapascals. So that's right here, 60 bars, 6 megapascals, and 540 degrees Celsius. So I can write down the volume and I can write out the enthalpy. Now, how do I know not to write out the internal energy? Well, I'm going to use the first law of thermodynamics of open systems at steady state. So I don't need the internal energy. If it was not steady state, I would, but I don't need it. So open systems use enthalpy. And you don't need entropy yet because we haven't done second law. So I'm just going to copy those over. And I'm going to, again, write them in SI units. So the tables give you stuff in kilojoules, which, keeping track of kilojoules and all these things tends to be kind of hard when you have so many working parts like here. And then the V bar is given as 0.06015 meters cubed per kilogram. Okay, so that gives us state number one. We have state number one completely filled out. Okay, what do we know about state number two? Well, we know that it exits the turbine right here at 0.008 megapascals and a quality of 0.9. That's all we know. So we know it's, and we know it's saturated, obviously. So I can put in the pressure here of 0.008 megapascals, which it's just 8,000 pascals. Okay, so it's going to exit at 8,000 pascal. That's P2. And then I don't know anything about these temperatures, but I do know, I'll put X here for the quality. This doesn't have any quality. And I know that this is 0.9. So what this means is that I can go to the saturated steam table, which is probably the first one, in pressure units. It's easier. And I'm going to go look for 0.08 bars, which is equal to 0.008 megapascals. And they even tell you here how to convert from 1 bar to 0.1 megapascal. 1 bar is 0.1 megapascals. So you can easily convert to bars because in bars. So now I know the temperature. That's easy. So I know the T2 is, and I'm going to transcribe that here. It's 41.51 degrees Celsius. And that's going to come up a lot more. Not that we use it for the actual numbers, I don't think. And then, how do I get, so it's 0.08. I have the volume of the liquid here. I have the volume of the gas here. And I also have the enthalpy of the liquid here and the enthalpy of the gas here. Okay, and I have a quality of 0.9. So again, to remind you, if I'm trying to find the V bar at this point for this mixture, it would be 1 minus X times V of the liquid plus X times the V of the gas. Okay, so X is 0.9, so that would mean that I have 0.1 times this thing, 1.0084 times 10 to the minus 3. 4 times 10 to the minus 3 plus 0.9 times 18.103. And that should give me the volume here. It should give me V2. And I can follow the same exact thing for the enthalpy. And then I would just put 173.88 instead of this number. And I'll put 22577.0 instead of this number. And I would get that. And you punch it into the calculator and you get that enthalpy for state 2 ends up being 2336.7 times 10 to the third joule per kilogram. And my volume is 16.29 meters cubed per kilogram. So you could see, as we expected, that my volume increased significantly through the turbine by 2 orders of magnitude or so. And you can also see that the pressure went down a lot and the temperature went down a lot, which is also consistent with what we said. State 3 is also saturated. And state 3 is saturated. And we know now that it's completely in the liquid state. So X here is 0. Okay. And we know from this that it's at the same pressure and temperature. So it's going to be 8,000 Pascal and 41.5 degrees Celsius. What about the H and V? Well, if I go back here, now I'm only in the liquid. So just take this. This is the liquid volume. So it's 1.0084 times 10 to the minus 3 meters per kilogram. And my enthalpy is 173.88. So it should, I just transcribe it over. So this guy here is 173.88 times 10 to the third joules per kilogram. And the volume is 1.0084 times 10 to the minus 3 meters cubed per kilogram. Okay, now when going from state 3 to state 4 through the pump, what you should know is that it's adiabatic. You should know that it's at the same temperature. Temperature doesn't change. You should know that the volume doesn't change because we're going to assume it's incompressible because it's a liquid. And you should also know that, well, the quality doesn't count anymore because it's no longer saturated. It's just a liquid. You should know that you really can't look this up at the table. So, so what do you call that? Yeah. So you can't find H. You do know that the pump restores the original pressure. That's the point of the pump. So it's going to go back to P1. Okay, so P4 in these cycles is always the same as P1. So we have that. So now we have almost everything defined for us. We really need H4. We will find that. So we don't have H4. We'll find it. Okay. Now, as far as the processes are concerned, and the processes will really give us what we need. Okay, we know that the work of the turbine and this the specific work of the turbine, not dot. I'm sorry, it's not per second. Just the work of the turbine, the specific turbine work. This is going to be, and it's always the case for these things. We're gonna neglect kinetic and potential energy, and it's going to be H2 minus H1, just the negative of it. Well, I have both of them, so I could put it in. So I know that if I put it in, I have 1180.3 times 10 to the third joules per kilogram. Okay. I also know the specific work for the pump is also from the first law analysis, but it's always going to be the case. This. Okay. I don't have H4. We will get back to this in a second and discuss what to do with this. As far as the specific, the heat per mass of the condenser is going to be equal to H3 minus H2, which again I have, H3 minus H2. And you expect this to be negative because you're releasing heat. You get 2162.82 times 10 to the third joules per kilogram. And also the heat for the boiler, which is really going to be a big one, that's heat boiler is H1 minus H4. Okay, again, we can't do that because we don't have H4, so we will need to get that. Okay, so to get H4, and we'll get that, we'll then use that afterwards. To get H4, okay, what we know is that the work of the pump, okay, is negative change in enthalpy between states 3 and 4, right? As we said here, it's just a negative of that change from 3 to 4. Okay, so we've defined enthalpy before as the integral of CV dt, which is delta U. This is just delta U, plus V VdP plus PdV. Okay, that is enthalpy. Okay, and just to remind you, even before we even get that, enthalpy was defined as this: H, big H, is U plus PV, and so if you want DH, it's du plus pdv plus vdp. That's just the, and this is just the definition of enthalpy thermodynamically. I'm applying it for our specific case. So no longer d's, it's deltas. So it's with integrals. Okay, what do I know about the specific change from state 3 to state 4? First of all, the temperature doesn't change. So what that means is I can get rid of this thing. No CBDT, delta U 0. Okay, so that means that the internal energy also doesn't change. Okay, I also know that the volume doesn't change because it's incompressible. So that gets rid of that for me. Okay, basically, since the volume is constant, if I were to integrate this thing, which I need to, I forgot to write the integral, the V bar would come out. So what this means practically is that this is negative V bar 3 delta P from 3 to 4. Okay, and that's how we can calculate the work of the pump. And then from that, we can get delta H, okay? So we know the specific volume is right here. It's 1.0084. And we know the change in pressure, 1.0084 times 10 to the minus 3 meters per kilogram. And we know the change in pressure because the pressure 4 is 6 times 10 to the 6th, and the pressure at state 3 is 8,000. So we can just put that in. Now, and you can see why I kept it in SI units, because now we're going to have a situation where we're multiplying pascals by meters cubed per kilogram. Well, Pascal times meters cubed, that gives us directly joules. So we don't have to worry about any the kilojoules or whatever. So I'm going to put that in, and I arbitrarily picked V3, you could put V4 because it's the same thing. And so we know that it's 1.0084 times 10 to the minus 3 meters cubed per kilogram. There's a negative there. We put that in. Negative, it's equal to the negative of that times the change in pressure from 4 to 3. So we have 6 times 10 to the 6 pascals minus 8,000 pascals. Okay, so now we get the work of the pump. And so that actually solves that thing here. So if I punch all this in, I get negative 6,042. So this guy right here just ends up being negative 6,042, 0.0, I think. Yeah, 0.0, sure. Joules per kilogram. So now I have, no, I'm sorry. Did I do it right? I think I forgot to times 10 to the third. No, I didn't. That was correct. Negative 6,042 joules per kilogram. Okay, just like that. Sorry. So now I have the work for the pump. I have the work this, I have this, and now I need to get H4. How do I get H4? Well, now I know this, and I can relate it to H4. So, sorry, H4. So I know that negative 6,042 is equal to negative H4 minus H3. So from work pump equaling negative 6,042 joules per kilogram equaling negative H4 minus H3. Well, these two negatives go away. Okay. And I know H3, and I also know H3 in joules per kilogram. I know that H3 is 173.88 times 10 to the third joules per kilogram. So I will put that in. So I have 6,042 joules per kilogram is equal to H4, which is what we want now, minus 173.88 times 10 to the third joules per kilogram. And from that, we get H4 is equal to 179.92 times 10 to the third joules per kilogram. Cool. So now we have that. Okay. So it was a little bit of a loop to get that, but it's not so bad. And of course, I did it slowly. So you can follow. I bet you could do it a little bit faster once you get the hang of it. So now we have H4. So I could put that here into my table because that completes it, and I like complete things. So 179.92 times 10 to the third joules per kilogram. And obviously I had to calculate that. Okay, this wasn't given to me. Okay, so now we have the work of the turbine, the work of the pump, the work of the condenser. We don't have the heat from the boiler, but we do have H1 and H4 now. We have H1 is 3517 times 10 to the third, and we have H4 is 179.92. And so we can get now quite easily the heat from the boiler. And if you punch that in, you should get 3517 times 10 to the third joules per kilogram. Okay, so now we have all the specific versions of the heats and the works that are required. So if you look at this sketch again, we know how much heat we're putting here, how much work we're putting here, how much heat we're getting out, how much work we're getting out. We know all states, 1, 2, 3, and 4. But we don't know is the specific, sorry, we do have the specific, but the actual work, because we have Q, little q, we don't have big Q, which is what we want. We want big Q dot, we want big work dot. Okay, so that's sort of like the next thing we need to do. So we kind of delineate that by putting a line through. So what we need now is to get the mass flow rate. Once we get the mass flow rate, we can multiply all of these numbers by the mass flow rate, and we get work dot and Q dot. So we just need the mass flow rate. So what we know from the question, and the only number I really haven't used yet, go read it again. So I have stream number 1 flows into a turbine, and the turbine produces this much power. So we haven't used that fact yet. So let's use it. So if you know work dot of the turbine, because we know that already, we know that work dot, I'll switch colors, why not? Okay, so we know that work dot for the turbine okay, we know that this is equal to the mass flow rate times little w of the turbine. Okay, and we know the flow rate, the work, the power that we have that's being produced by the turbine, it's 10 million watts, and a watt is a joule per second. So we know that this work turbine thing on the left side is 10 million joules per second. Okay, and we know that that's equal to m dot, which we don't have yet. And we have the work from the turbine that we calculated up here as 1180.3 times 10 to the third joules per kilogram. We put that in times 1180.3 times 10 to the third joules per kilogram. Okay, so what that means is now we can solve for m dot, and it will give us kilograms per second, because the joules will cancel the joules, and the kilogram will go to the other side, and we'll get kilograms per second. So when we put all of that in, we get our m dot is actually not that high. It's about 8.5 kilograms per second. I mean, it's high enough. So we have about 8.5 kilograms per second as our mass flow rate. Okay, so if we go back to the actual question, what they asked us, we only just solved part A, but solving part B is easy because we did all the legwork already. So now, work dot a turbine, work dot for pump, work dot for condenser, work dot for boiler. I just take this number, 8.47, and multiply by each of these, and that should give it to me. Why? Because if I multiply kilograms per second times joules per kilogram, the kilograms will cancel and I get joule per second, which is what I want. Now, going back to big work dot a turbine, that's silly because it was given to me. So I don't really need to do that. But if you do it again, it will just basically give you that again. So we know that big work for the turbine, well, that was given as 10 million watts, joules per second, or watt, okay? We know that the work for the dot for the pump, well, that's gonna be little work for pump times m dot. Little work is negative 6042 joules per kilogram. Okay, so I'm just gonna delineate this particular one, and then afterwards I will just show you. Negative 6042 joules per kilogram times 8.47 kilograms per second. And so the big work dot for the pump ends up being negative 51190 watts. Okay, so now we have the work for the pump, we have the work for the turbine, and we need to get the heat for the boiler, which again, what we will do is take this number, 3517 times 10 to the third, and multiply by 8.47 kilograms per second. And when we do that, we get 28,273,000. Oh, did I overdo that? 273,000, yeah, 76.6 watts. So you can see we have to put in a lot of heat, a lot. And the heat that evolves out of the condenser, again, you take the heat of the condenser and you multiply this by 8.47, and you get negative 1,832,4276 joules per second. So a lot of heat comes out of there as well. Okay, so so that's that. Okay, so we just did part B. And lastly, we're asked for what % of the boiler heat input is converted into net work. Okay, so this kind of acts as a cognate of efficiency. So we'll call this efficiency. And it's net work. So what we're going to do is we're going to get work of the pump plus work of the condenser. We get the total work. And we're going to divide that by the heat from the boiler. So basically it's asking how much of this heat got converted into work, total work. Okay, and obviously you have to put some work into the not condenser, I miswrote that, pump and turbine. Turbine, okay, so we're gonna get this number as a positive work value because that's what we got. Work pump, we have to input work and we have to input heat. So when you put that in, you get negative 51190. Because you have to put in work into the pump, okay? And then you produce 10 million watts from the turbine, but you have to input 28 million watts into the boiler. Okay, and these numbers will cancel. These are all in watts, okay? So the units will cancel, and times 100%, obviously. And we get 35.6%.